Multiple current carrying wires 2. Two wires carry different currents in the same direction. So here we have our two wires. They're carrying different currents. There's a certain length of each wire. They're a certain distance apart. What symbol would we use to indicate the direction of the magnetic field generated by I1 at the location of wire 2? Here's a current there, I1, and that's going to generate a magnetic field around that wire. In what direction does that magnetic field act at the location of wire 2? Well, we would use our thumbkin twist and right hand rule. We're pointing our thumb in the direction of conventional current, and then you can see our fingers here would curl right there at the location of wire 2 into the page. That would be a magnetic field that's into the page right there. Thus, what's the direction of the magnetic force on wire 2's moving charges? Wire 2 has some moving charges here, and those charges are moving through a magnetic field that was generated by these moving charges. Well, we've said that that magnetic field points into the page. And in what direction will there be a force on those charges? We're using our pat right-hand rule now, where our thumb, you can see, is pointing in the direction of I2. Our fingers, indicated by the nails, are pointing into the page, as we just figured out in letter A. And which way will there be a force? Right down here in the lower right, you can see I've drawn an arrow there. The force is going to be to the left. There'll be a magnetic force in that direction on those charges. What symbol would we use to indicate the direction of the magnetic field generated by I2 at the location of I1? Let's use our thumbkin twist and right hand rule again. We're going to line those up with the way I2 is going, and which way would our fingers curl at the location of I1 towards us? The magnetic field is directed towards us right here where I'm pointing. And so those charges are going to feel a force because they're moving in a magnetic field. And what direction will that force be? Well, that force is going to be, according to the pat right hand rule, our right thumb is going to point in the direction of the current. Our fingers are going to point in the direction of the magnetic field. And which way do you pat? You can see the arrow down at the bottom of the screen. It pats to the right. The magnetic force acts that way. So you can see that when the wire currents are going parallel to each other in the same direction, it's going to be an attractive force. See that? They're going to pull towards each other. And if one of the currents were going opposite, then it would be a repulsive force. It's an easy way to remember. If the currents are going with each other, they're going to attract. If they're going opposite each other, they're going to fight. It's kind of like people. If you're working with someone, you're going with somebody, you're going to become drawn closer to them. You're going to have a closer relationship with them. Whereas if you're wanting one thing and somebody else is wanting another thing, that tends to push you apart from each other. Maybe that's a way that you can remember that. From our answers above, we see that parallel wires conducting currents in the same direction exert an attractive force, parallel wires having oppositely flowing currents a repulsive force. Let's write expressions for the magnetic field at wire 2's location due to I1. We have used many times that the magnetic field at a certain distance r away from a current is given by mu naught times the current divided by 2 pi r. How about the magnetic field at wire 1's location due to wire 2? There you go. These don't have to be the same current, by the way. They can be different. Now, what about the force on wire 2 as a consequence of the magnetic field at 2 due to current number 1? Well, whenever we had the force, you might remember this equation, IL cross B, and here everything is at right angles to each other. So in essence, the magnetic force has a magnitude of I times L times B. If we want the force on 2 due to I1, we're going to take the current of I2, we're going to take the length of the wire, and then we're going to have the magnetic field at that location, which is this expression at the top of the screen. U naught I1 over 2 pi times R. Now, what about the force on wire 1 as a consequence of the magnetic field there due to the current I2? Well, it's the same equation, but now we're talking the force on current I1 that'll multiply by L. Now, the strength of the magnetic field at wire 1's location is right here. Mu naught I2 over 2 pi R. Now look at that. How do those two compare? You got an L, you got a mu naught, you got an I1, you got an I2, and in the denominator 2 pi R. Those babies are equal. How come we're not surprised that those are equal? Because those are an action-reaction pair, Newton's third law. Even if the currents aren't equal, doesn't matter if the currents are equal or not equal, doesn't matter. The force on each wire, one on the other, is going to be the same. All right, let's finish with a numerical example. Feel free to stop the video and do this on your own. I'm going to go through it extremely quickly. Here we have two wires. They're a certain distance apart. There's a certain length of the wire that we're dealing with, and we want to know what's the force between these two. First of all, is it attractive or repulsive? You can look at the diagram and you say, hey, they're both going in the same direction. That's going to be attractive for sure. End of story there. What's the magnitude? We're going to use that equation that we just derived. Again, stop the video if you want to do this on your own. Mu naught is a constant, and since all of the units are correct here, as I've put them in, the length and the distance away were given in centimeters, but I changed those into meters. So I'm being a little bit lazy and leaving the units off of this expression. But anytime we hit equals on our calculator, you always have to put units with that. You can do a little bit of canceling with the pi if you want to, but if you type that in, you get a pretty tiny force of attraction